Hello students. Today we are going to learn about packing efficiency in solids. In whatever way the constituent particles, those particles could be atoms, molecules or ions, are packed there in always some free space in the form of voids. Okay. Now these voids are the spaces in between the atoms, molecules or those entities. Packing efficiency is the percentage of total space filled by the particles. Let's calculate the packing efficiency in different types of structures. Now we have the drawing of packing efficiency showing cubic close packing structure CCP. Okay, let's see what is the efficiency of this structure. We have this cubic structure and these are few atoms which are shown separately. This one is at the edge A and the other one is at this place, okay, C. Now there is one more in between these two atoms. Now we can see that this structure has three atoms, this drawing, and now if we consider one edge to be A and this diagonal AC to be B in length, then in that case we will be getting the calculating the values of packing efficiency. So here we have this calculation of packing efficiency in HCP and CCP solids. HCP stands for hexagonal closed packing and CCP for cubic closed packing. So the first thing we must have in our mind is about efficiency. What is packing efficiency? Let's see. Packing efficiency is equal to what? Volume of the sphere in unit cell upon total volume of unit cell. Now whenever there is calculation of percentage, the value is always multiplied by 100. So I put it here. This is packing efficiency. It has to be calculated in percentage wise. So now let's begin our job with calculation of packing efficiency in HCP and CCP solids. First of all, let's talk about how many atoms are there in unit cell of HCP or CCP. There are always 4 atoms that are connected to it. So we can say that there are 4 atoms. Let me start. 4 atoms in a unit cell. Of what? HCP and CCP. This you already know, you have already calculated. So we are using those values over here. Therefore the packing efficiency will come here again. We will take count of those 4 atoms. So now the formula will become volume of how many? 4 spheres in unit cell upon now again the main value is not changing, that is total volume of unit cell, and again this will be multiplied by 100 because it is about efficiency. this is initial of the calculation. Now let's begin our next job. Let the side of a unit cell is equal to A. We have already taken A, or let's assign AD equal to A, because all sides are equal, they all are equal to A, and here the diagonal AC is B. What about this? This side is also A, because all are equal. So again, let us assign it. Let the side of unit cell is equal to A. And what is the value of diagonal? And the diagonal AC. Where is AC? This is A and this is C. This is equal to B. Okay, we are done with it. Now let's see in triangle. There is one triangle is forming. Which one? There now in triangle, say ABC. Where is ABC? This is ABC. Again, we all know this is A and this is also A. So in ABC, what we know already? We know AB is perpendicular. How? These all sides are perpendicular to each other because they are forming a cube. So AB is perpendicular, DC is a base, DC is a base. In case of triangle ADC, let's see ADC, which will be better. So, and then another case, AC. AC is, what is AC? AC is diagonal. You can take any of this triangle. Actually I was taking ABC, but it was inverted. So now ADC, it will be clear for you to read. So it will be better for us to take ADC. So now let's see what is there. According to Pythagoras theorem, let's apply it. AC square. You all know AC square is equal to the sum of square of AD plus square of, which one is remaining? DC. DC square. So now let's put their values. AC is equal to B, so it's B square. AD is equal to A square, and then we have DC. This is also equal to A square, and these values are coming to be B square is equal to 2A square, or if square is left, then this will be turned into what? Root 2A square, or it can be rewritten as what? A can be taken out, A root 2. Now let's consider this value to be the value of B, and now proceed further. Let R is the radius of sphere. तो क्या होगा? What will now happen? So B will be equal to 4R. How? If this is equal to R. radius of this sphere. Another sphere is there. It has this diameter, which can be written as 2r, and this is r. So r plus r plus r plus r will be equal to 4r. B is equal to 4r. Thus, we have two different values of b. We have this one and this one. They can be equated. B is equal to a root 2 and then equal to 4r. This value, this can be equated, and from here we can get a is equal to 4r by root 2. That is what we are getting. So let's proceed further. Now this can be written as a is equal to 4r by root 2 and multiplied by root 2 to get a is equal to 4r. This is 1. Root 2 by root 1, root 2 is equal to 1. So this can be written as like this, and these values will turn into 2. And now this 2 can cancel this 4 to form a is equal to 2r root 2. Let's consider this equation to be equation number 1, and now proceed. Again, we are taking another value. Now, volume of cube. We all know it is side cube. So we are getting a into a into a, or simply a cube. And now substituting this value into the desired equation, volume of cube, this is the value of a. So this comes to the putting the value of from equation we will get volume of cube is equal to how much? Let's make it 2r root 2 cube. Now volume of sphere, this is our another equation. You can take it equation 2. So let's proceed further. Now volume of sphere, we all know how much? 4 by 3 pi cube. We all know this equation, and we also know 1 unit cell of CCP or HCP contains 4 atoms or 4 spheres. So volume of 4 atoms or 4 spheres, volume of 4 atoms in CCP and HCP is equal to 4 into 4 by 3 pi r cube. This is their collective volume. Now packing efficiency. Let's see what is the packing efficiency. Packing efficiency. we'll take these values. Volume of 4 spheres. What is the value of this 4 spheres volume? 4 by 3, 4 into 4 by 3 pi r cube, and divided by volume of total volume of the unit cell, which is how much? This volume of the cube, this cell, 2r root 2 whole cube. Now this value will be multiplied by 100 to get efficiency. So when calculated, this is going to be 4 into 4 by 3 pi r cube, and taking cube of these values turn out to be 8 into r cube into how much it will be? It will turn out to be 2 root 2 remaining, and then this will be multiplied by 100. You can calculate this, multiply by taking cube of all this value. Third power. Okay. Now this, when calculated, will come out to be cancelling the r cube, and this 2, and then it is 4. All the calculations, then this will be by putting the value of pi 3.14 into 100, this 100 divided by 3 into what is the value of root 2? Root 2 is 1.414, and after calculation it comes out to be 74%. So what will be written over here? Thus, you can say that packing efficiency of HCP or CCP structure is equal to 74%. Now let's study about efficiency of packing in body-centered cubic structures. We have the diagram of such structure. It has this atom which is situated inside the cubic structure, and it is surrounded by other atoms. This is body-centered sphere. Now these 3 spheres, which are arranged in diagonal arrangement, touching each other, since they are equal in size, they have radius r. So the length of this diagonal AF would be r plus r plus r plus r, that is 4r. Now let's calculate efficiency. So in a body-centered cubic unit cell, one atom is present in body center, this one, and apart from 4 atoms, they are at the corners. Total sum on this value will come to be 4, and their contribution will be then halved, so that total number of atoms present in body-centered unit cell is equal to 2. One for this and one for the other remaining spheres which are contributing some part into the cube. So now let's start. Side is A for this cubic cell also. A. Okay, now let a unit cell BCC, body centered cubic, We have already assigned the side to be A. Now let's check what is the diagonals. Let's start with FD. Take it to be B. Take it B. Diagonal, the other diagonal is AF. This one. Take it to BC. Radius of atom present in unit cell to be R. Now start. First we'll take triangle EFD, this one. So it has this hypotenuse, these two sides. ED and EF are perpendicular to each other because they are also contributing to the cube, whereas this diagonal is inclined to this. This is working as hypotenuse. So we can write that FD, this side, square of this side, is equal to the sum of the square of other two sides, according to Pythagoras theorem. Putting their values, FD is equal to B, it will be square. EF, let's see, EF is equal to the side A, it will be A square. ED is also equal to A, so it will be or B is equal to root 2A square, and this comes out to be A square root 2 . Now let's see in triangle AFD, this one, AFD has this hypotenuse and that also on this side. This diagonal is perpendicular to AD. FD is perpendicular because it is going through this section. So let's see. AFD, we have these sides. This is hypotenuse. So again, we can write AF square is equal to FD square plus AD square. Sum of these two, AD and FD. And this diagonal hypotenuse. Now we can write AF square. AF is equal to, we know, R plus R plus R plus R. How much? 4R. But now we are taking C. we will write C square is equal to FD. FD is equal to how much? B plus AD square. AD, where is AD? This is AD. That is equal to the sine. Okay. A square. You know, B square is equal to 2A square. This value can be placed here. So, this can be rewritten as or C is equal to root 3 square or taking A square out. Now, you already know C is equal to R plus R plus R plus R. So, we know that C is equal to 4R. You can write 4R is equal to A root 3. From this we can have the value of A. If A is captured, root 3 will be moved to other side and the equation will now become 4R by root 3. So we have value of A to be A is equal to 4R by root 3. Now the volume of sphere, we all know what is the value, and now before that let's take the value of volume of cube. Side cube is equal to A cube is equal to, putting this value, 4R by root 3 whole cube. And after that, let's calculate the volume of two spheres. No, their volume sphere. Why we are taking two? Because the body centered cube has on an average two spheres, total of two spheres. So volume of how many? Two atoms or spheres present in BCC is equal to, we will multiply 2 into 4 by 3 pi r cube. That's volume of sphere. Now let's calculate packing efficiency. Packing efficiency volume of net cell divided by total volume. Cell multiplied by 100, because this percentage. Now put those values over here. first will be volume of two spheres, 2 into 4 by 3 pi r cube divided by volume of unit cell, 4 r by root 3 whole cube. If this value is calculated, that will be this is going to be 2 into 4 8 by 3 pi r cube divided by how much? This will be 64 r cube by how much? 3 root 3. Into 100. Can cancel r and r and calculate further. These values are calculated, and now 8 into 0.14, so the value of 5 into root 3, 1.732 divided by 2 into 64 into 100 will be equal to how much? 68%. So we can write thus packing efficiency of BCC structure is percent. Now let's calculate packing efficiency in simple cubic lattice. Here we have such lattice in which we have these two spheres which is in front of us, and these dotted spheres are not highlighted. We know that if we take radius to be r, then this side, which is now we are taking a, will be equal to r plus r, that is 2r. So let's begin. Packing efficiency in SCC, simple cubic structure. So let's start. Number of spheres. You all know number of spheres in simple cubic structure comes out to be 1, because they are contributing their 1/8, so the total will be equal to, later on comes to be 8 in contribution. That means there is only one sphere, so volume of one sphere how much? That will be 4 by 3 pi r cube. Now we know volume of cube is side cube. This is the cube. Now let's total the side. You know, we are taking this side to be a, and every side will be equal to a, but there will be these points in where spheres are touching, having radius r. So a will be equal to r plus r. So side of cube comes to be how much? R plus R is equal to 2R. Now let's check packing efficiency. The formula is same, so we'll be putting values. Sphere 4 by 3 pi r cube. There is only one sphere, so we are not going to write any other number. And the volume of cube, total volume of cube will be a cube, or can be written as this value 2r whole cube, and then that will multiply by 100. So it comes to be 4 by 3 by r cube divided by how much? 8r cube, 100, cancelling r cube, and then we have these values. On calculation, putting the value of pi, the value will be 3.14 divided by this how much? 6 into 100. So the value will be approximately 52.33% efficiency. So we can write that the packing efficiency in simple cubic structure lattice is how much? 52.33%.